Greetings and welcome to Astronomy 104 at HAC. We've spent some time in class, we've talked about the history of astronomy, and one of the things that we talked about was Johann Kepler and his 3 laws of planetary motion. And I'm going to take a little bit of time here to go over those 3 laws just as a review for you so you can go back and review what we talked about in class and have something that you can review for future exams and the like. Now, recall, Kepler had 3 laws of planetary motion, and his first law stated that the orbits of the planets are ellipses with the sun at one focus. Now here we have to define what an ellipse is for this to make any sense. And the pictures here we have a circle on the left, which is what we're used to. That's what the orbits were thought. Before Kepler, these were the planetary orbits. They were all circles. So they were all circles before Kepler. An ellipse is a squashed circle, and you see an example of that here on the right-hand side. Now, the ellipse has a number of different parts. A circle is very, very simple. It has a center, approximately here, and that's it. And every point on the circle is the same distance away from that center. So in this, the planet would always be the same distance away from the star. That's not the case in an ellipse. In an ellipse, the focus would be someplace here, would be one focus, and there'd be another focus over here, and the planet would then orbit. The sun would be located at one of these. So let's say here. Here's the sun's location at one focus of the ellipse. So the planet would orbit and would sometimes be further away from the sun and sometimes would be closer to the sun. Now, these orbits are exaggerated. The orbits of the planets are all very, very close to being circular, but not quite. And it was enough that Kepler was able to, when looking at Mars's orbit, to be able to distinguish the difference and to be able to see that really they were not circles. And it finally got rid of that history of epicycles upon epicycles upon epicycles that we've talked about in class in order to predict the planetary motions. This made the prediction much easier for all the planets. Now, the other parts of the ellipse are the major axis, which is right across the center between the 2 foci, and this is the major axis. And we have the semi-major axis is half of that. So we go to the middle here of the ellipse. The semi-major axis would be half of this. That's the average distance of the planet for the sun, and we call that A. And we're going to come back to that again when we talk about one of the other laws. But A is the semi-major axis of the orbit. If this were a circle, that would be the radius of the circle. But that's an important number. The minor axis is just the axis going the other way through the center of the ellipse. And then we have the foci of the ellipse. The other number related to the ellipse is what we call the eccentricity. No, the ellipses aren't eccentric in that way that we normally think about it. But what the eccentricity is it's a number between 0 and 1. 0 is a circle, and 1 would be a parabola. It wouldn't even be an ellipse anymore. It would be an open end. It would be essentially half of an ellipse. It would be open-ended. The ellipse would never close again. So those are the orbits. Those are the primary orbits of the planets. It's somewhere between 0 and 1. Most of the planets are very, very close to 0. Most of the planets have a very, very small eccentricity. And that makes them very close to circular, and is one of the reasons why we were able to use circular orbits for quite a long time when we analyzed them. So that was Kepler's first law. His first finding when he analyzed all of the data that had been collected on the planets was that no, they were not circles. We can finally say no more circles. Everything is an ellipse. It's a squashed circle. And again, the one I've shown you here is greatly exaggerated. This would be more like the orbit of a comet. Comets have this kind of orbit that is this squashed, and they do come that close to the sun and go that far away. They can come into the inner planets and go way out beyond Neptune. So a comet might have an orbit that is this squashed. The planetary orbits, for what you could see, are going to look a lot like the circles. Now, Kepler's second law says that a line joining the planet and the focus of the ellipse will sweep out equal areas in equal times. And everybody loves this law because that makes so much sense, doesn't it? What does this mean? What does it mean? Well, let's put our sun in here at one focus. And what it means is that if we look at the sun, at a planet traveling around the sun, here, as it orbits around, if this takes, say, 1 month to move from this point to this point, then it's also going to take 1 month, say, to move from this point to this point. And what Kepler found is if he calculated this, if we did the calculation and we said that, okay, what area is here, that this area was the same here as it is here. Now, what meaning does that have? That still doesn't have a lot of physical meaning to us. Yes, it sweeps out equal areas in equal times. It's a very geometrical thing. But what does it mean is happening? Well, let's look. If this is 1 month and we had 1 month over here, what does that mean? What Kepler's second law is really telling us is that the planet moves fastest when it's close to the sun. So it moves faster when close to the sun. And obviously the opposite is going to be that it moves slower. The planet moves slower when further from the sun. So what Kepler's law tells us is that when the planet is closer to the sun, it moves faster in its orbit, and when it's further from the sun, it takes a much longer time to move through its orbit. That's all it is telling us. It's telling us about the speed of the planet. How fast is it moving? That's what Kepler's second law. So we don't need to think about this equal areas thing. That's how the law is defined. But really what it's telling us is that the planet moves fast when it's close to the sun and slow when it's further away. That's what Kepler's second law is telling us. Now finally, Kepler's third law tells us that the cube of the semi-major axis is proportional to the square of the orbital period of the planet. Another tough one, right? Not really so bad. Not really. All it tells us is that, remember, we had that ellipse. And let's bring an ellipse back up here. We can use that. And if we have an ellipse here, what do we know? We know the semi-major axis was the longest dimension of the ellipse halfway across the longest dimension of the ellipse. So from the center here, this is the semi-major axis. This is A. We can measure that. That's the average distance. So as we wrote before, A is equal to the semi-major axis. Now, P is just the period. That's another easy thing to remember. These are both easy numbers to get. Period is just how long does it take the planet to orbit. It starts here, and it goes around, and around, and around, and when it comes back here, that's 1 period. For the Earth, that's 1 year. So for the Earth, let's look at these numbers for the Earth. The period of the Earth period is 1 year. What is the semi-major axis of the Earth's orbit? Well, we talk about that in a number of different ways. It's 93 million miles. It's it's just that distance. So many kilometers, so many inches, so many feet, so many meters. Could do it in centimeters. But the one thing we use, and we define the distance, the average distance from the Earth to the Sun, to be 1 AU. And if we use this exact set of numbers, then not only are they proportional, but they're actually equal. And that means that if we use years in astronomical units, then a cubed is equal to p squared. And if we look at the example from the Earth, 1 cubed is equal to 1 squared. Well, 1 cubed is 1, 1 squared is 1, and hopefully 1 equals 1. But what that means is that for our solar system, and again, I'm limiting this right now for our solar system. We'll look at some other examples later on. If we know either the semi-major axis or the period, we can determine the other. Period is relatively easy to measure. We can measure how long it takes a planet to orbit the Sun, and then we can figure out how far away it is. And that's what Kepler's third law tells us. Now, we're going to do a modification of Kepler's third law when we talk about Newton that will allow us to calculate the mass. And that's going to be very important in determining masses, and not just in the solar system, but elsewhere in star clusters, in galaxies, binary stars. We can actually calculate masses, and it helps give us some evidence for black holes. So, we've had a little bit of a review here, and that was the whole idea, was just to give you a little bit more summary and just kind of reinforce what we talked about in class with Kepler's 3 laws. So hopefully this has helped you to review that, and we will continue with some more of these videos just to help you and help to reinforce some of the topics that we're talking about in class. So have a great day, everybody, and I'll see you in class.